Michelle is out of town joining us remotely, so I'll handle seminar today. We have two speakers today, so we need to keep things moving. So I will introduce our first speaker. Kyle Kaskie is doing his master's with Mike Wimberly. He comes from an undergraduate degree here at SD State. Previous work with Game, Fish, and Parks, and he's been here since the early part of the year, back doing his master's. So Kyle will be speaking to us about mapping and risk assessment of juniper encroachment into South Dakota grasslands. Take it away.
Well, thanks for being here. Thanks for the introduction. Like I said, I am interested in mapping and risk assessment of juniper encroachment. A quick overview. We are primarily interested in two species, which include the eastern red cedar and the Rocky Mountain juniper. These species do have a very large distribution and live in a variety of environmental conditions, of which include an annual temperature range from 40 to 68 degrees Fahrenheit, an annual precipitation as low as 15 inches and upwards of 60 inches. These species can be found growing in areas with well-drained soils that have various slopes, rocky exposed areas, northern aspects, as well as abandoned fields, fence rows, and under power lines. This would be an example of a typical red cedar you'd see growing out in the grasslands. These are naturally occurring species with a native distribution for eastern red cedar. Across 37 states and 4 provinces east of the 100th meridian, while Rocky Mountain juniper can be found primarily in the western portion of North America at mid-elevations. Areas of overlap have shown some hybridization. Recently, red cedar has been receiving a lot of attention as its overall distribution and densities have increased. These are species that were once primarily restricted by fire, however have been expanding outwards into new unestablished territories. A long history of fire suppression and active planting have contributed to this overall expansion. Management and control efforts that have been implemented include prescribed fires as well as mechanical removal. However, these implements are best done during earlier growth stages. The landowners and land managers are the ones implementing these procedures, however, have a tendency not to do so until it becomes a time-consuming and costly matter. Currently, junipers can be assessed at a state level. For South Dakota, this is done through the South Dakota Department of Agriculture, where their 2016 forest report has estimated Rocky Mountain junipers at about 21 million trees and eastern red cedars at 19.2 million trees. They also have shown a yearly net growth of around 1.65 million cubic feet. These are broad assessments obtained through the forest inventory analysis, which uses random inventory plots. This can be an issue as junipers do have a distribution of fragmented and patchy areas, which has the potential of a higher error. Other assessment methods include land use and land cover data sources, such as the National Land Cover Data. However, here, to be classified as a forest, an area has to be larger than half a hectare and trees larger than 5 meters in size. If we do take a closer look at an example of a National Land Cover data set, we do see that they classify forests under deciduous and coniferous classifications. However, bigger issues consist of some misclassification that does occur, as well as the big issue is that a large portion of these treat areas do not even meet the minimum qualifications for the forest and therefore are not even classified. So that brings me to the objectives of my research, which are to evaluate the classification accuracy of juniper detection methods while using Landsat 8 medium resolution satellite imagery, and to develop a practical workflow for large-scale juniper mapping. As well, we want to model the distribution of these low-density juniper and determine the accuracy of risk maps based on the distance to seed source and environmental covariates. Our study area will pertain to an area of 13 counties across southeastern South Dakota, including counties bordering the Missouri River. This will come to a total area of approximately 22,000 square kilometers. Concentrations of junipers are primarily down along major water features, but some smaller patches do occur without. To begin meeting my objectives, I first want to ask, how does winter and non-winter imagery affect the detection accuracy of vegetation indices and linear unmixing methods when classifying juniper? For this, data will be obtained through Landsat 8, which is a passive sensor. Images are radiometrically and geometrically corrected, as well as calibrated to surface reflectance. With this, we're able to obtain the multispectral images, of which we can reference reflectance in the shortwave, near-infrared, and visible spectrums. This will consist of bands 2 through 7. Landsat 8 was launched in February 11th of 2013, has a 16-day revisit period, and is at a 30-meter resolution. We want to obtain multiple images for the scenes in path rows 3030 as well as 2930. This will consist of winter imagery with snow cover and non-snow cover, in addition to images during the growing season, primarily May and June. There has been multiple methods for forest classification, and most recently, which have looked into juniper classification, of which we will be using the vegetation indices threshold. This is a 2 to 3 band ratio, such as the normalized difference vegetation index and enhanced vegetation index. These are measures of greenness, and we do have the luxury of juniper being a coniferous species, of which they retain their needles or leaves in a level of greenness during the winter periods, while other vegetation becomes dormant or dies off. We also want to inspect more advanced methods, such as a spectral mixture analysis. This has been used to determine the abundance of materials within a multispectral image based on the material's spectral characteristics. Here it can be assumed that a pixel contains a linear combination of the reflectance of those materials. For this, we'll obtain in-members by selecting either unique or extreme spectral values that are then referenced to the materials of interest. For example, we see here, if we look at a spectral graph, we do have fairly good spectral separation with our trees, as well as water and snow. We then want to apply these methods to the multiple images obtained to determine the best of classification. Here it can be assumed that images of more uniform desire will have a better overall spectral separability. For example, if we take a closer look at a snow-covered image, we can see that the snow has a potential of acting as a masking feature, of which the juniper and the treed areas become the dominant feature on the background. If we do compare this to a non-snowed image, we do see there are multiple features in the background, as well as some potential areas of different levels of greenness, which in the end will conflict with our classification. For validation, this will consist of a stratified random sampling design, where our strata are allocated across our study area to a closed canopy, a buffer around the closed canopy, a non-forested, and shelter belts. This will consist of approximately 1,500 sites, or 1,500 samples per scene, which are proportionally allocated to the area. These samples then are referenced to the Landsat 8 pixel, which can then be converted to a 30 by 30 meter polygon, which then can be referenced and delineated with the use of high resolution imagery, such as that obtained through Google Earth and MAVE. This delineation will consist of obtaining vegetation and landscape types, as well as juniper presence and absence and overall densities. A secondary validation measure will take place, which will include a subsample of the previously allocated sites, along with driven transects, which are going to be ground validated. This will consist of approximately 250 sites, along with 1 kilometer driven transects. These areas will be focused in high concentrated juniper areas, as well as based upon accessibility. Investigation of the site will consist of a GPS confirmation points, photographs, as well as recording of vegetation characteristics such as species composition and growth stages. A final accuracy assessment for our methods will be obtained by using a confusion or error matrix. This has been used to predict the total, the producers, and the users' accuracies. This is obtained by taking a stratified random sample where the strata are assigned to our map classes. So in our case would be Juniper and non-Juniper. We have attempted some preliminary tests, which I have here broken up into 4 categories. We have seen some overall high detection probability for Juniper down to around the 20% range. As we do see though, as that density does decrease, so does our detection rate. To begin meeting our second objective, we'll begin wanting to first ask where are the primary environmental factors contributing to the distribution of Juniper across our study area. For this, data will be obtained with Juniper presence and absence points, the use of a digital elevation model, a PRISM model for climatic parameters, land use sources such as National Land Cover Data Set and undisturbed grasslands, as well as water features and soil surveys. Here, our analysis will take place with the use of a logistic regression model in our statistical software. Our explanatory variables will contain an elevation, aspect, slope, mean annual temperature and precipitation, land use, distance to water body, and soil type. Our response variable will then contain the Juniper presence and absence. Here we'll build our models by adding the explanatory variables and then examining the effects of each addition while investigating the added variable and partial residual plots. Next, we want to determine and ask what areas across the landscape are of high risk of Juniper establishment. As I previously mentioned before, we do know we have a high detection probability for these areas of high density, high concentrated Juniper spots. However, as we get into these lower density areas, our detection rate dramatically decreases. For that, we want to come up with a secondary modeling for this. For this, we'll obtain data through the low-density Juniper presence and absence points, in addition to our Landsat Juniper map. We will also use the previously mentioned data sources such as the digital elevation model, PRISM model, the land use data sets, our water features, and soil surveys. Here, again, analysis will take place with the logistic regression model in our statistical software, where our explanatory variables will contain the previously mentioned parameters in addition to a distance to establish Juniper. Here, our response variable will then contain the low density Juniper presence and absence. Model validation for our binary dependent variables will be performed using a heat map plot and heat map statistics in the heat map fit package. Here, a heat map plot takes our predicted probabilities against our empirical frequencies and then draws a heat map line. We then can obtain a p-value by comparing the original heat map line to a parametrically bootstrapped distribution. After a final model is then obtained, we are able to project that across our study area and then obtain a site-specific risk assessment. Some considerations as we move further with this research. Primarily, we are working with a 30-meter resolution, and this has a potential effect for our lower detection rates on our lower density areas. Additionally, we have a potential limitation of obtaining the adequate imagery, as Landsat 8 was launched fairly recently in conjunction with our bi-yearly high-resolution imagery data sources. We were working with about a 3-year period of time. Obtaining the adequate winter imagery is also affected by cloud cover and limited snow coverage. Additionally, as we go into our risk model, we want to use this as a prediction of Juniper occurrence and not as a overall distribution source. A schedule has been set in place for the spring of 2017. I established our study area as well as began our sampling design. For the summer of 2017, I began collecting validation points for Scene 3030, as well as began testing our overall classification methods. For the fall of 2017, we will begin collecting our validation points for 2930, as well as the ground validations, and begin our accuracy assessments. As we roll into the spring of 2018, we'll begin finalizing our models and adding any other details that needed. With that, I'd like to acknowledge my committee, Dr. Mike Wimberly, Dr. Josh Leffler, and Pete Bauman, as well as SU Geospatial Sciences Center of Excellence for funding and resources. And with that, I would like to take any questions.
environmental variable that affects the distribution of juniper is people planted them in shelter belts.
Yeah.
And even when they aren't planted there, birds poop out the seeds, and so they're very abundant in shelter belts. Is there a way to pick apart that as an environmental variable?
Yes, I think I'm gonna have to approach it as doing our natural distribution versus the planted areas, because we're gonna try to capture those planted areas. But the problem that we found was that a lot of these planted areas are of smaller areas, so we're not capturing the whole areas with our 30-meter resolution. So that was one potential issue. But the way I'm trying to approach that is by adding those land use data sources, and we got the undisturbed grasslands is our main focus too, but looking at there is a source of junipers here, and then so what's going on around that source. If there's agriculture, any other sources going on, then there's probably a low potential of that being spread. However, if it is a undisturbed grasslands or a CRP area, then there's probably a higher risk of that being a potential for spreading that disease. That's how we would like to approach that.
So, if I understand correctly, the distribution or dispersal of this juniper might depend on the, say, the parental plants, the age of these parental plants. So, were you able to, put this information into your model in terms of the age of the established plant and what that will affect the?
Not fully, but how I guess we are attempting to do that is that we do know that these are spreading really fast. If they do spread, then I think it's like as little as 30 years they can become a total closed canopy, of which we know that those are the areas of higher age classes. So that's pretty much a majority of the areas that we are picking up with those higher density areas, so we can treat that. For the dispersal part, that's more of, they do have a low dispersal rate based upon the actual parental tree themselves, that the majority of success of these establishments are through fruit or birds and stuff like that. So we know that, but the majority of those birds actually have a small home range. So then we're able to determine or look at it as potentially around the seed source as the potential risk. So I guess kind of got a little off there, but that makes sense.
Can you go back to your objective slide? I just wanted, is it clear that you're not trying to understand how juniper is spreading? It's just, you're just looking for it, right?
We are just looking for it, but we want to assess what the pattern is for this area. As it is, since there is such a large distribution, all those previously, I guess you'd say, parameters that are for its growing, I guess, it's just been focused on wide areas, and all these studies have been either a small area or, I guess I'm getting a little wrapped up there, but yes, we're just basically looking at mapping it, but if we can include the pattern, what's the pattern for this area is what we're trying to determine.
What, it's I guess and I don't want to be kind of jerk about this, but if you've got a little tiny cedar that gets going and you're looking at a 30-meter resolution, you can't find it, you can't see it. And so from just a pure basic ecologist, you want to go out and find these little guys and then kind of understand what it is, why they're getting established, etc.
Yeah.
So it's kind of like, it's like the early phase of something. Once the cedar gets probably 2-3 meters, it's obviously there, it's
Exactly.
easy to detect, but it was more like what happened 15 years earlier. I mean, I drive around range country all the time, and I see you know, just driving on the interstate, you see little guys like that tall, and you're thinking, oh man, they're gonna be in trouble in a couple of years. And, you know, so to me, it's like, what's the mechanism? I think
Yeah.
Dr. Johnston already said it, you know, it's the shelter belts, the seeds, the birds, the deer, et cetera.
Yeah.
And it's more or less what is the preventative things to stop it? Because otherwise it should just spread like wildfire.
Yeah, that's, I guess that's why I'm probably about a 2 years too early, because they're coming out with new sensors, new sources for these satellites that are, you know, at a 10-meter resolution, but they're still too early to obtain good images. However, how we're trying to approach that is by using our risk model and saying that we do know that there is a short distance from these areas, that the land use is a big factor, and what are these other maybe slopes or anything other that may be adding to this, so then we can be able to go to an area and say, well, we know we have a defined patch through our original Landsat map, and say that we do have cedars here. Well, then what's the risk of the surrounding area of it actually spreading by using the risk map, and by using those other factors?
Yeah, I mean, the classic example is if you just go west of Mitchell, there's a field that has a you know, hedge of cedars, and I've watched it over the years. The trees get in there, they get real tall, then they come out and they wiped it out, and then you just watch it happen again. And so it's just, it kind of, you know it's gonna happen.
Yeah, like this is a perfect example, I would say, from at images back in the 90s. This area was cut off right here, and these junipers were about back to here, and there was a small patch that looked like this that was right here. Well, in about the mid-90s, they actually came in and fenced this off right here, put in a water tank, and then began doing some heavy grazing in this area. Well, then over the years, you can see that this was fairly limited for spreading. However, this pretty much took off. And then I don't know if they missed a year or two of grazing or something, but then all of a sudden this just exploded here, so you could actually see, just like you said, just some effect of land use changing that it's affected that spread explode outwards.
Yeah, and then, you know, if you go down I-29 south of Sioux Falls,
Oh,
and
yeah.
you get into those hills before you cut over to Vermillion, same thing.
Yeah.
All right, we've got a second presentation, so let's give Kyle a round of applause.